Okay, let's do an example on this one. So what we got a summation n equals 1 to infinity of an, and then we are going to approximate that with Sn, which equals the summation little n equals 1 to big N of a. And then what was left over, the stuff that you neglected or threw out, was the summation n equals big N plus 1 to infinity of an. Okay? Again, Rn starts at n plus 1. And we found out that Rn is less than the integral from n to infinity of f of x dx if f of x is decreasing, continuous, positive, and f of n equals an. Okay? If all these are true, then that bound is true. Let's do an example. So let's pick the summation n equals 1 to infinity of 1 over x to the fifth. Does this series converge? Yeah. This is a p series. P's 5. 5 is bigger than 1. So I know this series converges. To what? I'm not sure. But let's get a bound on it. So what my boss wants to know, he wants to make the error when I do this guy less than 0.0001. So I want to approximate this guy with an error less than that much. How do I do that? Well, what do I do? I'm going to approximate it with S. How big? I don't know. I need to figure out what big N is going to be. And I know that the error is going to be equal to Rn, but I don't know what N is. So I need to do, and this is less than the integral from wherever I'm going to start to infinity of f of x dx. Now I got to figure out all the pieces. What I really want to know is how far I have to go out to get an error less than this much. Okay, so let's do this. Okay, I got to figure out how far I need to go to do my approximation. But I do know that Rn is less than the integral from n to infinity of f of x. What do you think we're going to use for f of x? Sorry, that's supposed to be n to the 5. Kind of getting ahead of myself. This is the function we're going to use is x 1 over x to the fifth. Okay, is this function positive? Yep. Is it continuous? As long as we stay away from 0, and where n's bigger than 0, so that's going to be continuous. Positive is decreasing. Yes, I'm taking numbers bigger than 1 to higher to the fifth, so it's going to be getting, this bottom's going to be getting bigger, so the whole thing's going to be getting smaller. It's continuous, it's positive, it's decreasing. Does it match the sequence at each one of the integer points? Yeah, you stick in a 1 there, what are you going to get? You get the same as that 2. So it matches all the things you need for f. And now we just got to figure out what n has to be. But I got to make this guy less than 0.001. Let's just take the integral. What's this integral going to be? So that's going to be the limit as b goes to infinity of the integral from n to b. I'm going to write that as x to the minus 5 dx. What's that going to be? The limit as b goes to infinity of, do this, add 1 to the 5, you're going to have x to the minus 4, and divide by minus 4. Does that work? Multiply by minus 4, we're going to kill that guy, take 1 off, get a minus 5. Yes, that's the proper improper integral. And so it's going to be n to b. Okay, so now we take the limit. B goes to infinity. Put the b in. I'm going to pull that 1/4 out, so it's going to be 1 over minus 4. And that's going to be 1 over b to the 4th power. And this is going to be minus 1 over minus 4. And we're going to stick in the n. Okay, so that's going to be 1 over n to the 4th. So make sure you believe that. Okay, that's sticking in the limits of your integral. Now, what happens is b goes infinity. Well, b is going to be a really big number. Taking fourth power is going to be even a bigger number. So what's going to happen here? This is going to go to 0, and you're left got two minuses. So this is going to equal 1 over 4 times n to the fourth power, and I got to make that less than 0.0001. Now the bigger n gets, the smaller this gets, so I'm just going to solve an equation first. So I got 1 over 4 n to the fourth, set that equal to 0.0001. Okay, I'm going to multiply both sides by n to the fourth and divide by this quantity. So when I do that, I'm going to get 1 over 4 times 0.0001 is equal to n to the fourth, and I'm just going to take a fourth root of both sides. Okay, I'm plugging that into a calculator and hope I can do it right. I like being in class and have y'all help me out because I screw up all the time here. Okay, so that's going to give me parentheses 1 divided by parentheses 4 times 0.0001 close parentheses, and I'm going to raise that to the open parentheses 1 divided by 4, close it, enter, and I get, when I do that, I get that n equals 7.071. Okay, now n's going to keeps going on. Now n's got to be an integer. I got to stop somewhere. I can't stop at 7 something, but I want it to be better than it has to be. So I'm going to let n equal 8. Okay, so what does that say? To have an error less than that, all I need to do is take 8 terms of this guy. So I'm going to say that S infinity is similar to S8, which equals A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 plus A8. And if I did that, and if I threw away 9, 10, 11, all the way out to infinity, my error is only going to be at most 0.0001. Okay, so that's how you use the integral test to kind of help you with error bounds. If you can find a function that matches this guy, is decreasing, continuous, and positive. And again, this only works on positive series that have positive terms. Okay, that's it on this video.